Okay, so here is an example, and as we recall before, we had Euler buckling and we had Johnson buckling, and wanted to know the Euler is going to be long and slender, and the Johnson is for intermediate size columns, and we want to. So when we do a problem, we want to first check and see whether it is Euler or Johnson. And I think this first one is Euler. Okay, so let me see. Where'd you go? There we go. So, and this is a problem from Philpott. And we're starting out with a section, a wide T shape. I don't really like how that thing is focusing like that. Structural shear shape, and that's Appendix B of that other book, as used for the 6.5 meter column. Assume that we have pinned connections, so it's a pinned joint at each end. We want to find the slenderness ratio, the Euler buckling load, if we assume steel with a 200 gigapascal elastic modulus, and we want to find the axial stress of the column. So it's a good thing to kind of like just take a kind of a overall gauge of like how much force is this, right? But first, what we want to do is we want to decide whether we should get the Euler buckling or use the Johnson. And trust me, it's going to be Euler. Here's the properties of this structural shape, and I went ahead and added in to our blackboard somewhere a useful links and resources, and I found a couple of places, not very many. Okay, so here's the United States American structural shapes that we've used this one previously for assignment, like I think homework 1. Here's some old books. I wish I never had my own copy, or maybe I did have for a while. But anyway, of these old ones that the steel companies used to give out, because I was doing ship design and there's always picking out structural shapes. So it was always nice to have. I think I borrowed one. And but here's like an online one for American ones, and these are like old books from like 1948 and like 1926. That's funny. And here's tools for engineering section 2. So this one seemed pretty good, except it doesn't have any figures, right? So it's just got a long list. These are metric shapes, I should say, SI shapes. But they have a lot of them, but they don't really quite tell you what any of these parameters are. So that's kind of a shortcoming. And then I found this thing here, and I think I gave the link to, yeah, okay, so I gave a general link. We could go to shapes and properties, and I think here's the WT. Will I get to the right spot? Yeah. So I could pick out the one I wanted. So here's the WT 205, somewhere here. WT 205, I guess it's way down there. Oh no, did it not show here? Where's the 205? Come on. These are all really small ones. Did we go for, what are we going here? Why isn't it? I think these are inches. Oh, these are Americans. I want to go to kinetic general, maybe. Structural shapes. Come on, why are you doing that to me? Canadian. Let's go Canadian. Maybe these are Canadian. I'm learning as we go through here. I will keep looking for a good shape, right? So there's one. There you go, metric. So Canadian. It's Canadian. This must be a Canadian website, I guess. Anyway, here's our WT 205, right? So it does have American and metric on there. But we go to this, and you can see the actual dimensions. So it's 205. They say it's actually 204. Why'd they name it 205? I don't know. They left off a millimeter. But that's the depth of the thing, and 178 is the width. Here's one that was important to me, the distance from the neutral axis to this, and we had 46.1. We also have the web thickness. This is the web thickness, and here's the flange thickness. But so anyway, you can look that up. that's a good thing. Okay, so here's the other things of the problem. But I gave you the structural section properties right in here from the book, and one of the important ones is the moment of inertia, and they're doing crazy millimeters fourth. I don't like that, but that's okay. We'll figure it out. The moment of inertia about the x-axis right here, and then the moment of inertia about the y-axis. And you can see that the y-axis is weaker than the x-axis, right? Or it's smaller. Therefore, it will buckle about the y before it does about the x, right? And we could do that with our I-beam kind of thing, right? And I will pass this around in class, where you can see that it's harder to bend it this direction than it is to bend it this. That one is a stronger axis. This is a stronger axis about the x in here than it is about the y, right? So if that's the y, it's much more flexible. Its moment of inertia is smaller, so it will buckle that way first, right? And then we have these other properties, which we should probably compare. Let's see, they got the same area. I hope they have the same area right over here. Let's see, get the same area. I hope so. Where'd you go, area? I don't even see where the area is here. There you go, area 3,800. Sure. Okay, good news. Otherwise, what are you going to do here? And moment of inertia in x 13.9. And once again, they're doing the millimeters squared, but let's fix that. Okay, so here are our parameters, and so we looked up in the table, and then this is the guy that we're going to want to use right here. Also the area, and once again they did millimeters squared. So first things first, we're going to check this L over K. You go, well, which one is K? Well, K is going to be this right here. They decided in their book this is the radius of gyration in about for the y-axis, and you could check that if you wanted to by taking their moment of inertia and dividing it by area and taking the square root, right? So if we took our 5.99 e to the 6 and divided it by 3,800 divided and take square root, you would get 39.7, 39.6. So this is actually K, right? And so in the and we could check, actually, I think I checked it twice, but we could take this 6.5, this is the length right here, and divide it by, and remember this is in millimeters, so 0. Okay, this is not 1, sorry, this is just the slenderness ratio let's say about the y-axis, and 396. And we get 164.1 is the slenderness ratio. We could also check, if we wanted to, about the x, 6.5, and divided by here's the radius of gyration on the x-axis. What? Not 60.2, but 0.0602. And we get it's 104.8. All right, so this is the largest slenderness ratio, right? So so in this pin-pin condition, we won't do the effective length method. We'll use the C method. There's a pin-pin means C is going to be equal to 1. Therefore, I'm going to take my L over K, 1, which was equation 2 pi squared CE. Oh, and for this, I'm going to have to find a yield strength, right? So they decided to use structural steel, I think. So to use structural steel, yeah, as a structural steel section is a type of steel, and for that we can look it up. I'm just trying to find it somewhere. Where did I decide? I decided that the yield strength of structural steel is 250 megapascals, right? And we can look that up later to see what kind of steel that was, but that was 250. So we take 2 times pi squared times 1, because that's the end conditions. Elastic modulus, they told us to use 200 gigapascals, so let's go 200 E9, divide it by 250 E6, right, and take the square root, and what we end up finding is we get 125.7, right? So this slenderness ratio in the y-axis means it will buckle, it is larger than this slenderness ratio. Therefore, we should use Euler. Notably, for about the x-axis, it's actually less than this, and therefore, if we were doing it about the x-axis, we could show you why that could happen. We would use the Johnson equation to try to figure out what the critical load was when buckling occurs. But here's a slenderness ratio that we're asking for in part A. For B, we want to find the critical load here. And so I decided to use this one equation. I didn't use the slenderness ratio one, but we could do that too. Squared EI over, it says this is Euler, right? Over L squared. So we have 1 pi squared 200 E9. I is, okay, so I made the conversion. The conversion ends up being, so the millimeters is to the third, right? It is minus E minus 3, but we raise it to the 4. So what I said as a conversion is we have 1 e to the minus 12 times millimeters fourth will give us meters fourthed, right? So if they tell us that it's e to the 6 here, then 5.99 and then minus 12, and they go e to the minus 6 will be the conversion. So that's useful because people do use the millimeters fourth often for things. And do I need to put anything in there? No. We get 6.5 is the meters, and we end up with 280,000 newtons, or 280 kilonewtons. That's a lot, right? And then, so if we want to have the critical stress, that's just going to be the critical over the area, critical force over the area. And so we take 280,000, and they tell us that we have 3,800 millimeters squared. So we know we would need to take that e to the minus 6, right? Because millimeter is e to the minus 3, but it's squared. So we go 388 right here, e to the minus 6, right? Will give us that area. And then I get 73, and I'm going to go ahead and divide by a million again. So kind of comes out the same. But anyway, that's going to be megapascals. So that's interesting right there, compared to 250 is the yield strength, but here's what the stress that's experienced in the beam at failure right there. We could even say if we want to have a safety factor, which we'll discuss soon, is just going to be the strength over the stress. So 250 divided by 73.68 is going to be 3.39, right? Is the safety factor. If we're saying, and it's really, in this case, it's not quite a safety factor. It's not. It's just saying a ratio, but it's similar to the yield strength safety factor onto the thing, just to assess. It will fail in buckling according to this, and it actually will fail at a lower value than this. And we could mention, because this is an idealization, right, of the failure, and if it's just slightly over to the side, and for the load from the center, if it's just over, not exactly at the centroid, it'll cause buckling earlier. I think I have enough time. I have to go to a meeting here soon, but I wanted to introduce there you go. So here you go, a little FEA, a little finite element analysis. So I have made this section, and I'm in millimeters right here, and you can see how long and slender this is. That's a good educational part of the thing. And I'm in SolidWorks. I've made these little lines right here so that I could grab a hold of a spot to try to simulate a pin-to-pin connection. It would actually be kind of difficult along the x-axis to do it, but I did it along the y-axis, both at the top and the bottom of here. But you can see how long and slender this thing is with the proportions they gave us. Now, I've already done this once, so I know it works, but I'm going to create a new study right here, and this is going to be a buckling study, right? And so this is, by the way, this is linear buckling, so it's not terribly advanced. I'm going to pick a steel here, apply a steel. I decided to go with this carbon steel because it's like 200 gigapascals, right? It's saying 2e to the 11. That's the equivalent there, right? So I applied it so that material's on there. I can tell that it is because I put it. It shows up right here. For the fixtures, now I got to be really careful here. On the bottom of this, I'm going to grab it right along these two lines right there, right? But along the top, I don't want it moving. I want it to only move up and down. So I need to take, for my fixtures, an advanced fixture. So I'm going to grab these two lines again. But now I'm going to get a reference surface, and I'm just going to use this as the reference surface. Okay, and I wanted to let it go up and down. So the one that shows it as perpendicular, which is this bottom one here, you can't quite see it maybe, but you can see these other radio buttons. I'm going to go this way, so it's not going to let it go in the Z direction, and I'm not going to let it go this way, so it's not going to allow it to go in the X direction, but it can go in the Y direction. All right, so that's an important thing. I'm also going to just, because it could like decide to go diagonally, right? So I'm going to try to restrict it from going diagonally by putting in one more advanced fixture in here. And I'm going to grab this surface, and then I'm going to use that same surface as the reference. And now I'm not going to let it go into the page, right? So it can't go anywhere along there. It can't go into the Z. So that means it's got to buckle in the X direction, right? So there's a chance it can go diagonally some, and the computer might find that out. But we just want to compare to our hand calculation results. That's our main goal here. And so I'm going to put on the load onto here, and I'm going to put it onto the top. And I'm going to put it onto all, because I've divided it up into 4 surfaces. I'm going to put them on all 4 of them. Dang, I didn't mean to get that edge. I want to get the face. There you go. And it's going to be the total. And the way this works for the buckling thing is you just put on a unity load, right? Just one load. And it's that same load, I put it as the total. So there's just 1 Newton, by way of the way that this thing is doing it, across that whole thing. And then lastly, I need to create a mesh. I'm just going to accept the default. And this is not a great mesh, because there's not a lot of elements through the thickness. So, but let's go ahead and hit the old run button. Let's see what happens. I know that it'll run, but I think it runs actually pretty quickly. And here we go. This is what it looks like. There's the deformed shape. You can kind of see. That's what it looks like. It buckled, sure enough, about that axis. And you take a look up here in the corner. It's very small, I know, through the video. I don't know if I can make this any larger. I don't know if I can. Let's see if I go to this right here and I make that big right in there. So maybe you can see that they have the answer to this thing is 2.8052 e to the 5. That's 280, right? Right here. So here we go. Here is the critical buckling right there. That was actually part B. So we got 280,000 newtons is the answer. So there's a demonstration of using the buckling feature. Now this, I had to make a lot of decisions there, so just hitting the solve button when not thinking through all the boundary conditions will give you bad results. But this is another example of simulation in action in our course.